Sampling distributions. Today we're going to continue our discussion of sampling distributions, and more specifically, we're going to discuss sample proportions and their sampling distributions. So today we'll be talking about P's and p-hats, and we'll also look at standard deviation. Okay, so that's the notations we'll be using. Remember, p-hat is a sample proportion, and p is a population parameter. Okay. Now, also recall that for sampling distributions, any statistic, being a random variable, has a probability distribution. And the probability distribution of a statistic is sometimes referred to as its sampling distribution. So remember, when you hear the word statistics, we're talking about x bars or p hats or s's or s squareds. Okay, those are statistics, and they all have sampling distributions. And today we're going to focus mainly on the distribution of p hat. Recall our example of taking a sample from the population of people, adults, and we were interested in what percentage had blue eyes. And we had this graph in our previous lesson. The sample size was 100. We took 300 random samples. Okay, and every dot on this graph represents one of those samples, and the dots represent the percentage of people in that sample that had blue eyes. Okay, this was the mean of all of those dots. So if we took all of these dots together, put them in your calculator, and averaged them out, the average percentage was 0.092, and the standard deviation of all these dots was 0.028. Okay, so those are the results of this, our experiment, our meta experiment. We did the same experiment over and over again. Okay. Now, sampling distributions or proportions have special properties, and this is what we're really focusing on today. So, I have included our sampling distribution below the formulas. Our first formula is that the mean of all the p hats will equal p, the population proportion, which is a parameter. Okay. So when they mention the mean of all the samples, we're talking about all of these dots. Okay. That we found the mean of those dots, and that should equal the population proportion, or be very close to it. Okay. Our second formula deals with the spread or the sampling variability of all our samples. Okay. So this is the standard deviation of all the p hats. So again, I entered all of these dots into our calculator, all the values, and I calculate the standard deviation, okay, which we had on the previous screen. But this formula right here is a great estimate of that sampling variability. Okay, and you could say it is an estimate of the standard deviation, okay? So, and it's very easy. If we take p times 1 minus p, and remember those two have to add up to 100%, so they're complements, then divided by the sample size, and then we take the square root. Before we take the square root, that number would be the variance, okay? And then once we take the square root, we're talking about the standard deviation. So this calculation is a measure of that sampling variability, okay? Third property of sampling distributions is that if we take large enough samples, our sampling distribution will be approximately normal. And if we just drew a real loose bell-shaped curve around this, you can see it's pretty bell-shaped. It's not perfect, but it is, we would consider this approximately normal. Once we know a distribution is approximately normal, that allows us to use z-scores, okay? Where all we'll need is to know the mean and the standard deviation. And when we're using proportions, it would be p hat minus p over standard deviation. Because remember, p is our population proportion, which is the categorical equivalent to the mean, okay, population mean. And then p hat will be our sample, and then the standard deviation, of course, is the standard deviation. So taking large enough samples allows us to use the normal distribution. Okay. In order to assume the properties of our sampling distribution are correct, So those three things we just talked about, that the mean of all our samples should be the population parameter, and the standard deviation of all our samples should be p times 1 minus p over n, take the square root, and it should be approximately normal, okay? These three conditions must be met in order for those three things to be true, okay? So these are conditions, and we need to check these, okay? Like we have to run through this list and explain how we know that they are true, okay? Because once those are true, then everything we learned on the previous two slides comes into play, okay? So number one, the sample taken has to be a random sample. Number two, the sample taken is less than 10% of the total population size. Okay, we cannot go over 10% in our sample, and I'll explain why in a second. And the third thing is that n times p has to be greater than or equal to 10, and n times 1 minus p must be greater than or equal to 10. Now, some textbooks allow these minimums to be 5, okay? Depends on the author of the book, and statisticians go either way. Nowadays, most people seem to be going towards the greater than or equal to 5, okay? So for our purposes, we will use that going forward. Okay, now what do all those mean, and why are they important? Number one, the sample taken is a random sample. Well, if this condition isn't met, our sample will not be representative of the population, and we will get biased results. This is from a non-random sample. Okay, and what will happen is, when we average out all of those dots, which I'll do here in red, the average will be somewhere in the middle. Notice it's nowhere close to the population parameter. Remember, the bullseye is what we're looking for, the population parameter. Over here, if you look on the right, this is from a random sample. Okay, and when we get a random sample, then our sample should cluster around the mean, and if we average them out, we should be able to find the p. Okay, so we take a random sample to avoid this bias, okay? If we randomly sample, we should get our sample statistics right around the actual population parameter. Our second condition is that the sample size that was taken is less than 10% of the total population size. What this means is that when we sample, we want to be careful that there's independence between selections. If we draw more than 10% of the population, we are in danger of losing this independence. Okay? Imagine if we're drawing cards from a deck without replacement. Okay? Every card we draw changes the probability of the next card that's drawn. All right? And when we're selecting a random sample, we don't want that to happen. We don't want the fact that we chose person 1 to affect the probability of choosing person 2, etc. Okay? So in statistics, what they decided is that as long as you draw less than 10% of the total population in your sample, that we can still assume it's independent. Okay. For example, let's say I'm drawing M&Ms from this bag on the left, the small fun size bag. Okay. Maybe there's 15 M&Ms in the bag. Well, if I draw 2 or 3 M&Ms out of that bag, I significantly change the probabilities of the colors that are left inside the bag. Okay, and I want every draw out of that bag should have the same probability, let's say, of blue M&Ms. Okay, but if I choose a couple blue M&Ms out of that bag of only 15, I've really changed the probability of blue M&Ms in that bag, and I don't want to do that when we randomly sample. If you sample from a situation on the right, like a big jar with hundreds or maybe 1,000 M&Ms, drawing a couple M&Ms from that population is not going to change the probability of later draws. Okay, so if I draw 2 or 3 blue M&Ms out of that container, I have not significantly changed the chance of pulling a blue M&M in the future. Okay, and in statistics, as long as I don't pull more than 10% of the M&Ms from that jar, I can assume that that condition holds true. Okay, that I have independence between samples. The third condition, it was the n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. You can think of these as the expected value of the successes, and this would be the expected value of the failures. So what these two equations really mean is that if I can expect 10 or more successes and 10 or more failures in the sample I have chosen, then my sample is going to end up being, my sampling distribution is going to end up being approximately normal. Okay. And we mentioned that some textbooks use this instead of 10, that they say 5 is enough if it's 5 or more of each. We can use that condition on the AP exam. Either of them are acceptable, so you can do it either way. Okay. Now let's take a look at how these relate to our sampling distribution. Okay. First of all, this stands for the mean of all the samples. So up here, if I typed all these numbers into my calculator, I get a mean of about 9%, okay? Which, as we know, is the population parameter, okay? The 9% of the people on planet Earth have blue eyes, all right? So that's a really good way to find a parameter, is to find the mean of a sampling distribution, okay? And the big thing here is to realize that every sampling distribution, if done correctly, if I take the mean of it, it's going to equal the population parameter, okay? That is the main thing to take from that. The second thing is that I can describe the spread of this sampling distribution using this equation, okay? And all I need to know is what was the chance of success and how big was my sample size. So the standard deviation of the graph above should be equal to 9%, because that's my p, and then 1 minus p would be 91%, and my sample size was 100. So if I do that calculation, what I get is 0.0286, okay? So you could say that that's the predicted standard deviation of that graph above. And we know that it's basically the same as we got when we typed in all of these numbers into our calculator and calculated the standard deviation of that sampling distribution. They are the same, okay? So what that allows us to do is give a really good estimate of the distribution of our samples, okay? It lets us know, how much variation, sampling variability should there be between our samples. And then the third one, sampling distribution will be approximately normal if n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. And remember, you could use 5 for both of these as well. And I think I will use 5 in this case. So that means I would do 100 times 0.09, which is 9, and I would do 100 times 0.91, which is 91. So it means I expect 9 people to have blue eyes, and I'd expect 91 to not have blue eyes. And both of those are at least 5, okay? So because of that, this distribution, I can assume it's approximately normal, which simply means I can assume that a bell-shaped curve approximately fits it, okay? And remember, the great thing about that, once I'm approximately normal, is that I'm allowed to use z-scores, okay? So we're going to tie in that from Unit 1 as well. So let's do a problem related to this. So this says, suppose 9% of all adults have blue eyes. Suppose we randomly sample 100 adults. What is the probability that we get a sample proportion that is less than or equal to 6% blue eyes? So they've told us that all adults have, that out of all adults, 9% have blue eyes. So they're telling us P, okay? That the population parameter for blue eyes is 9%. And then it's telling us we're going to sample 100 people from that population. And what I want to know is, what's the chance that I get a sample that ends up being less than or equal to 6%? So on the picture, less than or equal to 6% is here. So I could actually figure out what was the probability of that happening inside of our 300 samples that we did. And that ends up to be 47 out of 300, or about 16%. Okay? So that means about 16% of the time, when we took our samples, we got 6% or less saying they had blue eyes. Okay? Even though we know the population mean is 9%, right? But 16% of the time we would get an answer that's in that green circle, according to our experiment. But we don't need an experiment if those 3 conditions are met. So let's run through the conditions real quick. Okay, so the conditions, and basically what we have to do is run through the 3 things that we talked about on that previous slide. We need an SRS, we need to follow the 10% rule, and we need n times p bigger than or equal to 5, and n times 1 minus p bigger than or equal to 5. So I need to show that those three conditions are met. And one way to do that would be to just tell a little story, write a couple sentences about this situation. So I will demonstrate that now. So we can say something like, they randomly sampled 100 adults. Okay, and how do I know that? Let's write in the sentence here. And then I can say, which is less than 10% of all adults. I think that's a pretty good, easy assumption to make, right? And then we can say, we expect to get 100 times 0.09 equals 9 people with blue eyes. And 100 times 0.91 equals 91 people without blue eyes. Both are greater than or equal to 5, so p hat is approximately normal. Okay, so I just basically spelled out those three, the three conditions, and I showed why they were true. Okay. Once we do that, that allows us to draw this picture. A bell-shaped curve, okay, because we know it's approximately normal. And we know by our first property that the mean of that distribution should be p, which is 9%. Okay. We also know that the standard deviation of that distribution should be p times 1 minus p over n, which is 0.0286. Okay. And then the question was, what's the chance I get a p hat that's less than or equal to 6%? Well, that would be here. And I would shade that in. So I can answer this question now using that information. Okay, and we will compare our answer to what we got from our experiment above where it was 16%. We'll see if we were close. Okay, so I would need a z-score. So remember to do 6% minus the mean divided by the standard deviation. Okay, and I would do that on my calculator quickly. And I get a z-score of negative 1.05. Remember, you can round z-scores to 2 decimal places. Then I will look up, using normal CDF, what percent of the graph would be below that. So that would be, remember, you type in negative 10 to negative 1.05. And when I round that answer, I get 0.15, or 15%. Okay? So according to the conditions and the situation that they outlined, we should find 15% of our samples tell us that get 6% or fewer blue eyes. Okay? And if you compare that to what we got when we actually did this experiment using simulation, it's very close to what we got in our experiment. Our experiment said this should happen 16% of the times, and our conditions and properties of sampling distributions tell us that it should happen theoretically 15% of the time. So very close. Okay, and that's the whole point of this, is that we do not need to run this simulation, okay? If our three conditions are met, we can answer this question using the properties of sampling distributions, okay? So it's kind of a way to bypass doing that meta experiment, okay, where we have to come up with all that data. As long as those three conditions are met, then we can proceed and solve this using arithmetic. Okay, let's do one more. So it says, suppose 9% of all adults have blue eyes. Suppose you randomly sample 100 adults. What is the probability we get a sample proportion that's greater than or equal to 15% blue eyes? Now, on the graph, 15% blue eyes is over here. Okay, and that ends up being 12 out of 300 people had that, which ends up being about 4%. Okay, so our experimental results were 4% of the time would we get a sample that showed 15% or more had blue eyes. But let's do this using our properties of sampling distributions. So again, remember our p-value is 9%. Okay, they've told us what the parameter is, and for this chapter, they're always going to tell you the parameter. Okay, this is how we are learning about sampling distributions. Sample size is 100, and I'm looking for samples that are bigger than or equal to, 15%, sorry. Okay, another way to go through the conditions, which we would need to do in order to use a z-score to solve this. Another way, you can just go through, instead of writing like a paragraph, you can just write 3 little sentences. Like one, they randomly sampled 100 adults. Okay, number 2, you could say assume 100 adults are less than 10% of all adults. Okay, and then our third one, we would say 100 times 9% equals 9, and 100 times 91% equals 91. You could say both are at least 5, so p hat is approximately normal. Okay, so that would be another way to run through the conditions. You could write just 3 separate sentences if you didn't want to do the paragraph way that I showed you in the previous example. But now we would, because we went through the conditions, now we can draw a bell-shaped curve. Again, put 9% in the middle, and because we know that the mean of p hats will be p. And we could also do the standard deviation again. We've already done this, but I'll just reiterate to emphasize. We do this equation, we get 0.0286. And this time I want to know what's the chance that p hat's above 15%. So 15% is over here. So that would be greater than or equal to 15%. So again, we're going to do a z-score. 15% minus 9% over 0.0286. So I find that z-score, and I get a z-score of 1.45. And then we're going to look that up using normal CDF. This time I'm going to go 1.45 comma 10 because I want to go to the right of the graph. So I go 10, and this time I get 0.07%. Okay, so that's the theoretical probability of this happening, okay, of getting 15% or more with blue eyes. You can see this time it was off by about, our experiment was off by about 3%, and that's okay. It's pretty close. And again, we would get better results if we wouldn't have stopped at 300 samples here. Okay. Remember, a meta experiment is unlimited experiments, or going on for an infinite amount of time. So if you'd done, instead of 300, maybe 3,000 samples, we probably would have been very close to that 7%. Okay. But just keep in mind, the idea here is that we can get a very good estimate of this probability without needing to run an experiment if our conditions are met. Okay. If our conditions are met, that opens us up to be able to use a z-score to answer questions about this sampling distribution. And it really comes down to, we want to prove that the sampling distribution is approximately normal so that we can use a z-score to answer these questions. Okay, good luck.